Alright, in a lab experiment, a group of students release a 0.6 kilogram wooden block from the top of a 0.4 meter tall wooden incline. Using a photo gate, the students determined that the block was moving at a speed of 2.2 meters per second at the bottom of the incline. Determine the gravitational potential energy of the block Earth system while the block is at the top of the incline. Alright, so here we have to think about what is happening. I'm going to draw a picture and realize that at the top of this block and at the bottom of the block, this is going to be our initial and this is going to be our final. So in the beginning, I can say that this block has some gravitational potential energy, and that's actually all we're trying to find right now. Just mgy. And the mass here is 0.60 kilograms. The g is 9.8 newtons for every kilogram. And the y, we're told, is 0.40 meters, that height. Let me grab my calculator. And then I see 0.6 times 9.8 times 0.4. And I get 2.35 joules of gravitational potential energy. B says, determine the work that friction did on the block while it traveled down the incline. A lot of people, when they look at this, they say work equals F delta X cosine theta. The problem is, I don't know what F is, and I don't know what delta X is, which is this actual displacement of the block. So, even though I know the angle between the force and the displacement is going to be 180, with these unknowns, I can't find work that way. So I need to think of another way to talk about work, and we can define work as the change in energy. Whatever energy you have in the beginning in your system, and whatever energy you have in the end, if there's any difference between those two, it's because there was some outside work. And in this case, I can say the final energy of the block is kinetic. It's down at the bottom, it doesn't have any gravitational potential energy, and there's no springs to speak of here. So the mass of the block is still 0.6 kilograms, and the speed, we're told, is 2.2 meters per second. And if I take 2.2 squared, times, I'll do 1/2 times 0.6 times 2.2 squared, I get a kinetic energy of 1.45 joules. And what that means is that there's energy that left our system, that this work, that friction did negative work here. That work would be the final energy minus the initial energy, which is the 2.35 joules minus the 1.45 joules, giving us negative 0.9 joules of work. And that is our answer. And then, is it positive or negative? It's negative. That makes sense because work done by the friction takes energy away from the system. And that energy doesn't get destroyed, it just transfers into heat energy, but the surface where a lot of the heat is not part of our system, so we can't include it as a type of energy. It's an outside work. I could also explain this by saying, look, the delta X is going to be this way, and the force of friction is this way. And the angle between those two is 180 degrees. And the cosine of 180 degrees is -1. So when you use this idea of F delta X cosine theta, these are just really absolute values. It's the negative from the cosine that determines if our work is negative. So negative work makes sense done by friction.